our group of NUS high school students.
I'm Jiamin, he's Dylan and she's Charmaine.
So today we'll be presenting on a project titled The Tolerance of Marine Copepods to Changing Salinity and its implications for Singapore's freshwater management.
As all we should know, Singapore has a lot of freshwater resources and as such we rely heavily on neighbouring countries such as Malaysia for water resources. So in order to increase our sustainability, Singapore actually has been damming up areas around the island, and one example would be the Marina Barrage.
Another would be the Punggol Dam.
Another is the Serangoon Dam.
Yeah, so what happens at dams is that when the gates of the dam open to release water, this actually result in a salinity shock. And as such, we in this project want to investigate the effects of salinity shock on the marine health. So we chose to use Copepods as a dominant Copepods as a representative species, as it's a dominant species in the marine ecosystem and also is food source for the highest street levels. So actually in this project we use 3 different sources of Copepods. There are typical Copepods from the Pandan River, as well as Copepods from the Pasir Mangrove Swamp and St. John's Island.
We collected Copepods using a plankton net and we cultured them using live plankton feed. We also collected natural seawater and prepared seawater of different salinities using a salinity probe. Then we prepared petri dishes and filled them up with seawater of different salinities. The control salinity will be the salinity that the Copepod was reared in. There, we placed 5 adult Copepods into each of the petri dish and 4 replicates were carried out for each of the salinities. We also carried out the same experimental procedure for each of the 3 types of Copepods. After 5 minutes and 24 hours, we then count the number of surviving Copepods in each petri dish using a microscope. Now I'll talk about our preliminary study. We took GERD Copepods and placed them into seawater from 15 to 25 ppt. After the eggs hatch, we then remove the mother Copepod and count the number of Copepods at each stage of the life cycle for 2 weeks. 3 replicates were carried out.
So now we move on to the results and discussion. So across all our experiments, we compiled all our results in these 4 graphs here. So the 3 bar graphs show the mean number of Copepods that survive across the salinity range from 0 to 40 ppt. And the first graph shows the number of Copepods for Tisbe Copepods. This one is for mangrove, and the last graph is for St. John's Island Copepods. So for the last graph here, it shows us the tolerance range of all 3 groups of Copepods across the salinity range. So for our experiment, we tried to determine the salinity tolerance of the Copepods across the range of salinities. So we found that the Pasir Mangrove Copepods and the St. John's Copepods have the same tolerance band, except the Pasir Mangrove Copepods survive better at the lower salinity, while the St. John Copepods survive better at the higher salinity. This is due to the fact that the Pasir Mangrove Copepods live at a lower natural salinity as compared to the St. John's Copepods. Overall, the Tisbe Copepods have the highest tolerance range, and we hypothesize that this may be due to the fact that they're actually cultured by the DHI lab for 6 months before the experimentation. So this may cause them to be more adapted to the natural conditions in the laboratory, as compared to the other 2 groups of Copepods, which are more freshly caught. So as for the next part of our experiment, where we try to determine the impact of immersion on the survivability of the Copepods, we found out that there was a distinct change in salinity tolerance from 5 minutes and 24 hours. So this tells us that the prolonged immersion in abnormal salinities actually cause the mortality rate of the Copepods to increase because they have to use up more energy reserves to osmoregulate. So as for our preliminary studies, we conducted a study on the 4 different stages of the Copepods. So we found that at 15 and 30 ppt, hatching success was low. And also we observed that at 35 ppt there was actually no nauplius hatching. So this may be due to the fact that at early stages of their life cycle, Coepod nauplius actually use up their yolk reserves to survive and do not feed. So by placing them in abnormal salinities, they have to osmoregulate and use up their yolk reserves, which place them in higher stressful conditions, which will lead to their death.
So there are a lot of ways in which we can improve on our experiment. Here are some of our ideas. We can investigate its salinity acclimatization, which can affect the mortality of the Copepods. We can create a setup in which water is gradually dripped in order to change the salinity. Or we can acclimatize the Copepods for up to 24 hours before testing them. Also, we can investigate if recovery in normal saline conditions will affect mortality. This will mimic the natural conditions of the dam, whereby after the dam opens, the seawater outside has a salinity shock, but it gradually returns back to normal. Also, we can improve on our current experimental setup by increasing the sample size or by investigating other factors such as age or gender will affect mortality.
So in conclusion, through this research project, we actually found that the Copepods have about 10 to 15 ppt tolerance range, and further immersions in abnormal salinity actually increases their mortality. Also, we found that the environment that the copepods are found, it affects the extent of their osmoregulation ability. So, in conclusion, our results actually show that the local population of copepods are affected by the changes by salinity shocks, and as such we propose that PUB should actually monitor the salinity conditions outside the dam and maybe release less volume of water each time so as to reduce the salinity shock and as such protect our marine ecosystem. Okay, so this is the end of our presentation. Thank you for watching.